Thanks for coming, everyone. I apologize if I look a little worn out. I just carried like 30 pounds worth of t-shirts over from the Bellagio. A little heavier than I expected, but they're here for you guys afterwards, so please come and get them after. Anyway, welcome to Punk Code, hiding shellcode in plain sight. I'm Michael Sutton. This is my colleague, Greg MacManus. This is a piece of research that actually stems back to work that Greg had done back in 2002 when he was looking at exploiting web browser vulnerabilities. We've certainly seen no shortage of that lately. You know, we just finished the month of browser bugs that H.C. Moore gave us. So we've seen a lot of it. But when you're exploiting that type of vulnerability, as when you're exploiting just about any vulnerability, one of the challenges that you face is getting your shellcode, and likely your NOP sled as well, into memory and then being able to find it. There's various techniques for doing that sort of thing. They have their pros and their cons. And one of the things that Greg thought of was, you know, why use one of these techniques? Why not use something that we know is going to be in memory, and that's the images that are loaded by the web browser themselves. But wouldn't it be cool if we could take that one step further and still keep those as images, so that they are a legitimate image, that if when somebody views it, it wouldn't arise any suspicion. So that's the purpose of this. We both work for iDefense Labs. It's a division of VeriSign, and the basis of what we do is vulnerability research, and that's where this came up, because you know, part of that is finding new and interesting exploit vectors. What we're going to go over today, we'll start off with just a very brief history of shellcode. It's important to understand why you would even need a technique like this in the first place, and then we'll get into what punk code is, how it works, what the methodology of it is. Punk code is not a thing. It's not an exploit, as Greg will explain. It's a methodology. It's a theory. But then we'll put that into practice. We'll discuss sort of how different images are created and how we can leverage that for our purposes. We've built some tools to make the theoretical practical. Those are actually up on our website right now, labs.idefense.com. Go in the software section. You'll see it, PunkGUI and JPEG-POC. We'll then sort of get into a little bit of theoretical about some other file formats that we haven't completed research in, and then talk about just some of the implications, both offensive and defensive, that arise from this sort of research. So here's my brief history of shellcode and buffer overflows. Buffer overflows have been around forever. It's not a new thing. They kind of came to light for a lot of people when Aleph 1 did his paper on smashing the stacks with fun and profit. And looking back, it's a pretty basic scenario, but it taught us the basic steps of what this is all about. Aleph 1 taught us what a stack-based overflow is. He taught us that we have to get our shellcode into memory, and in his case, he was using an environment variable to do that. He taught us that it's a whole lot easier to find our shellcode when we use a no-op sled in conjunction with it. And he also taught us that there's some challenges that we face. In the case of these simple overflows, it was that we couldn't have null characters, or we couldn't usually have null characters in our shellcode. And then lastly, he provided us with some basic code that took care of that, took those null values out. The vulnerabilities that were discussed in Aleph 1's paper, those were local vulnerabilities, not that exciting. You know, most people they're more interested in researching remote vulnerabilities, and that adds some additional complexities. We don't have as much control over the remote machine. We can't tell that remote application what to start up in memory, what to use as its environment variables. We also may have limited buffer sizes. And it's not just null bytes that we have to worry about. There's other things. If we're going in through a web-based interface, you know, we may be limited to using alphanumeric shellcode or Unicode shellcode, things of that nature. And lastly, then there's IDS evasion issues. You know, there's always this arms race that we're all aware of. The bad guys do something, the good guys do something, and IDS is part of that. The IDS signatures get smarter and smarter and look for things like simple no-op sleds. Where are we at today? Much more advanced state of affairs. H.C. Moore is speaking in one of the other rooms right now on Metasploit, and even the current production version of Metasploit 2.5, it already gives us 25 different payloads, 9 encoders. We're not talking about just launching a remote shell. We're talking about things like injecting a VNC server. So there's some pretty cool stuff. We also have tools that allow for automatic shellcode generation, and they take care of those encoding issues for us because we have decoder stubs that can decode and that can encode and decode our shellcode to get around some of these issues of limitations on what we can use. And lastly, we have fancy no-op sled generators so that we're not just sending a simple stream of 0x90s because those things are looked for, so we can be creative in what we send.
So what is pun code and how does that go in with all this? Well, pun code is a pun code. It's a pun being a play on words, and yeah, this is the same sort of thing. Basically, it uses the von Neumann architecture feature that data and code are indistinguishable to the computer. It depends on what you tell the computer to do with it. If you throw it at the screen, it becomes dots of colors. If you tell the computer to execute it, it becomes instructions to execute. The picture on the right is an image generated from an executable file. Basically, I just put an image file header on it and told it to display it. The code for that's on the left. Pun code is not a vulnerability or an exploit. It's just a method of putting the shellcode into the program. The code won't run without a way of actually calling it. And you can prevent being exploited by this by using hardware debt. I mean, but that's the same for pretty much anything which will which puts the shellcode on the heap and tries to execute it. So you need to make sure that's enabled and the current program isn't on the excluded list, and the memory permissions of whatever segment it loads the images into don't allow it to be executed, and then it would stop the thing. So pun code is actually a play on bytes. It makes images which are visual puns. They're entirely composed of a no-op sled and shellcode. They load directly into your browser. The tools that we're releasing allow PNG and JPEG format, and I've also done GIF format stuff. They look pretty much like a normal picture, and it's only slightly more work than embedding the shellcode into a large image file to get it into memory. You'll see what I mean, I think, when I show you by slightly later on. Yeah, we actually have exploit stuff that works with this. The first stage of research on this was back in 2002, not long before I started working for iDefense. I was looking at Netscape 6. They offered a browser bug bounty, a bug bounty of $1,000 for code which led to execution, for bugs that led to execution of code. So that was a good motivator. The code you see, the image you see on the right there, it's the stripes are some jump instructions, which basically, because most of the vulnerabilities I found were heap related, it was to jump over any of the corruption that occurred. First dark gray band there is to avoid the, is to stop, so it's something to jump into, so it doesn't jump partway into the code. And the colored stripes themselves are the actual shellcode. Because each line's exactly the same, it makes the stripes. So yeah, the question in the initial version was written, the answer was, how can I find my shellcode? When I was exploiting these vulnerabilities, I found that the web browser could be in any state at all. You didn't know where your code was going to be. It could have been running in any one of a number of threads. It could have started at any point. It depended on, were you loading a page in the background? Had you checked your mail in the last 10 minutes? I thought, well, how can I make the program use one fixed place? So with the way the malloc works is once a certain threshold is reached for the size, it uses mmap to allocate a region. And if you make the region large enough, it tended to be in a predictable space. It would, one of the return addresses, I could just use any return address which was in that range. So the way pun code works is you choose an image, you scale the image up a lot. So you want to make it take up a lot more memory because that gives you a lot more target to aim for. You convert the whole image into a no-op sled. Basically, you map each byte to a valid instruction, which doesn't do much. Then you embed the shellcode in it, somewhere where it's not too obvious. And you convert this into the final format. Certain compression caused by certain formats can damage the code, so you need to do some other tricks. So why would you want to use this method over, say, the Skyline's heap spraying method? His method fills a heap with a log run of 1 byte, which is the OD, followed by the shellcode, and then the exploit runs. The OD byte can mean a few things. It can either be the instruction or EAX OD, 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 which doesn't really do much except modify what EAX is. Or it can be a pointer to a memory address, which happens to be self-referential. So it's a safe address to reference, and it's safe to be dereferenced. So many workarounds for vulnerabilities only stop the exploit. Disabling JavaScript, well, I'll only stop JavaScript-based vulnerabilities. If the vulnerability is in another part of the code which doesn't require JavaScript, then you could use a different exploit method. It would prevent the Skyline heap spraying method, but it wouldn't prevent this method of putting the shellcode in memory.
Yeah, as Greg mentioned, what we're doing is we're taking that image and we're turning it into a NOP sled, but in doing so, we still want our image to remain as intact as it can. So the starting point was figuring out what instruction we can use, because we want to have bytes which are valid instructions, but at the same time, they also represent the pixels in the image that we want. So we had to first go through and say, what do we consider safe instructions versus unsafe? So anytime I keep referring to a no-op sled, and I'm probably referring to it in a sense that you don't normally think of it in, because we'll consider it a no-op as long as it doesn't affect code execution. So for example, a typical no-op is O by 90. But then take, for example, something like O by 42, increment EDX. That does something, it has a purpose, but for our purpose, that's a no-op, because it's not going to redirect the execution of our code so long as we're not relying on that particular register. So we have a much broader interpretation of what a no-op is, and that's important for us because the more bytes that we can use which are valid, the more accurate we can make our picture. There are, however, some things that we can't use. They're going to be unsafe instructions, things that require a usable stack like push, pop, call, return, anything which dereferences a register, and privileged operations. So we're never going to be able to make a perfect picture. It's always going to look like it's been degraded slightly because there's certain pixels that you just can't touch. So let's divert for a sec and talk about psychophysics. What the heck is psychophysics? According to Wikipedia, it is a subdiscipline of psychology dealing with the relationship between physical stimuli and their perception. What the heck does that mean? It just means the way we perceive things may be different than what they actually are. Think of when you go to the swimming pool. You go and you sit in the hot tub, it's nice and hot, feels really good, your body gets all warm. Then you get out and you run and you jump in the swimming pool. It feels ice cold. Is it really ice cold? No, it's so different than what you were just in. The same thing happens with images and what you look at. Depending upon the context of what you're looking at, you may interpret it differently than what it really is. That's important to us. You're not seeing the details. You're seeing the forest, not the trees. And that's good because it allows us to fudge things. It allows us to be a little less detailed without changing the overall picture. Go a little deeper. The eye is pretty forgiving. You can make little mistakes in a picture and they're not that noticeable. For example, if you have some pixels that are off color but they're really small, that's less likely to be noticed. If they're in the right spot, they're less likely to be noticed. Like they're on an edge. Like if you took a picture of me and the outline around me is an edge. If you have your shellcode in that location, because those aren't going to be pixels that are part of what the picture should be, it's going to be less noticeable. Also, just the way that colors are generated in a picture. As I'm sure most people know, you get a color palette by combining a small subset of colors, like red, green, blue. You combine those together in different ratios, and that's how you get your full color palette. And it's the ratio of the perceived brightness of each of those components that gives you the color. It's the weighted average of those components that gives you the brightness. And if you look at the percentages in that example, which makes a gray color, you can fudge with things that have less of an effect on the overall color than other components. So I could mess with the blue a little more than I could mess with the green before it would become obvious. And this is important to us because it allows us to make changes to a picture, and we are degrading the detail in that picture, but it's not that bad. You just think, oh, this person didn't know what they were doing. They did a bad job saving this. They did a bad job of using Photoshop. You don't think, oh my gosh, I'm looking at a bunch of shellcode. These are just some examples to sort of illustrate what I was talking about with psychophysics. So here's an image which at first glance might look like just a uniform color. And if you look at it closely, and it's probably harder to see with the projector, it's actually, the left-hand side is an 80% gray color. The right-hand side is white. And over the entire image, it's blended smoothly. So that helps, makes it look like a uniform color. Here we've only blended over 50% of the image. I don't know how well it's, yeah, this one I can see it. You can see that transition a little bit better. And here, I've done it only over 25% of the image, and it actually almost looks like a hard edge. It almost looks like two different boxes or rectangles. Here's another example. The background of those boxes is different. The bottom one is pure black. The top one is slightly off black. On their own, you wouldn't notice that. You would think that the top one was pure black. Same alternate flip side here. Top one is actually off-white. Bottom one is pure white. The eye can't really tell those differences, and that's important to us because it allows us to make changes that aren't as obvious.
Okay, one of the other important things to know is how images are stored. When you got a 2D image, when you see it, the computer only, because of the von Neumann architecture, only sees it as a 1D array of bytes. There's multiple different color encodings you can use. For images like grayscale, for black and white images, and that just gives you it's typically an 8-bit or 1 byte per dot. Red, green, blue, which is like what your monitors use. CYMK, which is for printing. YCBCR, which you might not be familiar with, which is what JPEGs use. It's also similar to what your television uses for the color. And index color encoding, where you actually look up a table of colors and you don't actually store the color values directly in the image, it's all indirect. And with compression, the files themselves can either use no compression, like raw full color bitmaps, or the PNM format, which we use a lot in the tools. Lossless compression, such as PNGs use the zlib deflate compression, which is the same compression as is used by gzip and also by pkzip's deflate method. And there's lossy compression, which JPEG uses some psychophysics to determine which part, they've determined which parts you don't necessarily need to see. And depending on your quality settings, after performing what's called a discrete cosine transform, which hopefully I can explain in a way that most people will get, if not, it's not all that important. It drops off a little bit of some of the values, and that's how it does the compression on those. And the file in memory is decompressed into a 1D array, which is the width times the height times the number of bytes that it takes to store each color. And then the contents of that can depend on the display color depth. So with your 24-bit color, it takes 3 bytes per pixel, 16-bit 2 bytes per pixel. The net PBM super format, or PNM, is a group of file formats which are used for storing images. On the right, up the top, is the actual contents of an image file. It's a really simple format. The top is the type of file it is. Then the next 2 values are the width and the height. Then it's the maximum value in it. And after that comes the raw data. I've chosen those particular values because the bang is the lowest character you can actually type and see come up on the screen, and the tilde is the highest one. The image underneath that is actually that image blown up a bit. It would be too small otherwise to see. We use this a lot as an intermediate format in the tools that we've developed. Another relatively simple format, but quite a lot more complicated than that, is the PNG, which is, we've got a header for the PNG itself to say the file type, then the image header, then the actual image data itself, which is compressed using the gzip, then an image footer, and every header has a checksum, a CRC32 checksum stored with it. Some other features which are supported and which are useful are the color correction mappings and the transparency. Because, some programs store the colors in 24 bits padded to 32 bits. Sometimes it just puts a random padding value of 0 or FF in there, and that makes writing shellcode a little bit more difficult. We haven't done that for our one, but because it's designed to work in IE. This file here is some random website I went to with, and I downloaded a GIF off it. We converted it to a PNM and scaled it up, so it took up 115 meg of memory. And we passed it through an early version of Punkui, which is the tool for converting to PNG that we've got on our website. And it came back as a 1.2 meg file. Now, is it loading? How do I do this? In the browser itself, is it coming up? It looks pretty much like the actual picture that you see on the website. If view image, you see which one I want? Which one's view image? That one?
At the very top.
Okay. This image is actually kind of big, as you can see. It's the full size. Over here, you probably can't see, but there's a few dots there. Yep. Yes. What that is the shellcode. The colored dots are the shellcode, and everything else is NOPs. And you just got to land before the shellcode, or it'll crash off the end. But you can usually hit it though by changing the location of the shellcodes or the image size, and you can just hide it in a place like that where you wouldn't see it.
So to further illustrate it, here's another picture of some guy that we found. I guess he's a hacker. And this first image is just a regular image, a JPEG image. But on the right-hand side is an intensity histogram, and it's on the y-axis we have the relative amounts of each color component. Then on the x-axis we have the intensity of the color components. If we convert that image into a GIF, you can see that the intensity histogram changes. A GIF only uses 256 colors in its palette, and so you can see our histogram now has all these gaps in there, and that's because we've gone from many colors to only 256 colors. So in theory, there should be somewhere fewer than 256 bars in there. This next image is actually a no-op sled, and you'll see again there's gaps in that intensity histogram. In this case, there's some bigger gaps. Let's actually blow that picture up and look at it in a bigger. So the one on the left is a regular image. The one on the right is a no-op sled, and you can see the quality is degraded. And in specific things that stand out, look at his arms. Like his right arm looks like he has some nasty prison tattoo on it. And knowing the history, perhaps that's real. I don't know. Above his head, things are a little bit weird. So you can see, and so why are certain pieces of that more degraded than other pieces? Well, the histogram on the last page, you could see there were bigger gaps there. Like right in the middle, there's some big gaps. That's because there's unsafe instructions in there that we just couldn't use. So that's just the reality of this technique. There's certain colors that you're not going to be able to access. So for example, in one of those gaps, it was that we had opcodes from O by 70 to O by 7F, which are jump short instructions, and we can't touch those because it's going to change code execution. We probably can't touch those. You know, a place that you could take this to make it a little more complex, a little more perfect, is that maybe you could use some of the values that we're avoiding. And the reason you could do that is, for example, you could not encode certain portions of the picture. Because again, all you need is a no-op sled and shellcode somewhere. So maybe the top half is that, and the bottom half is still a regular JPEG picture or PNG or whatever it is that you're using. So you could not encode the parts of the picture where you found that you didn't get a good quality image. Maybe you could use things like conditional jumps to actually jump around and jump over those portions of the picture which aren't properly encoded and have instructions which aren't necessarily considered no-op. So I mentioned already, now enough theory. We'll show you guys some demos. to actually, put this into practice. So we came up with a couple of different tools. I focused on a tool that worked on PNG coding. My job was easier because PNG is a lossless format, so it's not mangling my shellcode. Greg will discuss what JPEG does. It's a lossy version of image encoding, so it's going to mangle the shellcode. So he had to do a lot of extra tricks. So I took shortcuts. So Punkui is the JPEG one. JPEG-FOC is the JPEG one. Punkui is a C# application. It's a Windows GUI application. JPEG-FOC is command line, and it requires actually some other applications that it works alongside of. Yeah. So this is a video. Which isn't, oh, okay. Sorry, I gotta watch over here. So anyway, yeah. So on the left-hand side is where our original image is going to go. On the right-hand side is where our new image is going to go. So the first thing I'm doing is just selecting the initial image, and this is a real image. It can have any kind of. You can use a JPEG, you could use a PNG, you could use a bitmap file. The original image doesn't matter because we're converting it later. So this is a picture of some guy. I was at a wedding last year, and they put this drunk guy at my table. I think he works for Tipping Point. And this is just the original image. So it's just a JPEG image. So the next thing we want to do is resize that image. And you see the resize in megabytes, 32, 64, 128. You're thinking, that's a huge image. You can't possibly have something usable. That's the size that it will be when it's in the PNM format, which is the intermediate format. And again, we want to make a really big image. We want to make a really big image because the bigger the image, the bigger our no-op sled is, and the less obvious our shellcode is. Fortunately, the encoding formats like PNG and JPEG, they shrink it right down, so that 128 or 32 meg or whatever it is actually does become a very reasonable size to use on a website or something of that nature. So we'll resize it to a 32 meg size, and then it's just going to go through a series of phases. It's going to take that initial image, it's going to resize it and make it larger. It's then going to convert it to that PNM intermediate format, and that's the raw format, and then it's going to go through that PNM format and figure out which bytes are safe and unsafe, and make it into an image that it can actually use. And then it comes up on the other side. Again, we'll just look at it in a larger size. Also, you can see that there's just, I saved all the intermediate files. You don't have to do that, but just so you can see that, there was all the different ones that started. And then there it is. So again, it's a degraded image, but that is an image. It's a no-op sled now, except for on the right-hand side, you can see there's some stripes. You can let it go, and then just stop it once it gets zoomed in further. And so you can see down the right-hand side, there's a series of stripes there, and that's our shellcode. And the reason they show up as stripes is that every line is the same shellcode. So it doesn't matter where in the image that it lands, it's still going to hit the same, no matter what row it lands on, it'll still hit your shellcode. Like in the Black Hat logo example that Greg had, he just used one line because he wanted to hide it. And this is obviously less stealth by doing the whole thing, but easy to hit. And this is just a proof of concept. I mean, does that actually work? Is that a no-op sled? That shellcode is pulled straight from Metasploit, launches calc.exe. Does it really work? Yes, it does, but I'll save that for Greg's demo because he does the same thing, but he does it with a PNG file.
Yeah, JPEG files are not ideal for storing shellcode. They're developed by the Joint Photographics Expert Group for compressing photographs, which tend to have smooth edges and a lot of low contrast features, like where nothing changes too much over space. They're not appropriate for images with sharp lines and high contrast areas, like line graphs, cartoon images, or any image with fine details, and shellcodes of fine detail. The challenge is basically the lossy compression results in the loss of information, which definitely damages the instructions. It can be non-localized damage, just due to the way the compression algorithm works. The available instructions can depend on instructions which are several bytes away or several lines away, which can be several tens of K away in memory. One of the solutions, well, the solutions we tried for this were carefully hand-coding the entire shellcode so it would decode properly in a JPEG, which was very hard, and Windows shellcode's huge. The second method was to make a shellcode decoder stub and use that to extract the main shellcode and execute that. That's a technique which is used by a lot of other encoding methods. And I got that to work with some toy images. But if you change the stuff too much, it breaks again. You needed to have a lot of clear area around it. But then I tried to be a little bit smarter about it. Actually learning how JPEGs work before trying to abuse them helped a lot. A JPEG is how it gets encoded. Basically, it typically gets stored in YCBCR format, color space. The Y is the brightness, and that's the most visually important part. And the CR and the CB, that's the complement of red and the complement of blue. And it tends to drop information out of those to increase compression because your eye doesn't see so much in the colors. So basically, after you've broken them apart into the color components apart, you break each of those images into a series of 8x8 pixel blocks. Then, on each of those blocks, you apply what's called the discrete cosine transform, and then you do what's called quantizing the results. And you end up with a list, which is then Huffman encoded, which basically gives you the compression some of the compression that JPEG does. Then you add the required headers and the Huffman encoding tables, and you've got your JPEG. The DCT provides a list of values which tell you the amount each frequency contributes to the image. It basically breaks it from being basically breaks the space it's in from being the position into the frequency space. That formula there is kind of complicated. I have a picture an animation I think, which demonstrates it if I can find the mouse cursor. It's on the top left is the picture it's aiming for. In the top left corner of that thing is the picture as it's got to so far. The parts that it's made of, as it's moving along, you see this is where it's actually up to in the bottom part of the image, which is the table of coefficients for that particular block. And the pattern that's moving in with the stripes and going in each direction is the basis function for the discrete cosine transform that it's producing at the moment. And the black image in there is the difference. How it compresses it is it takes the coefficients from that bottom thing and divides them by the quantization factor, which is just a number which has been chosen pretty arbitrarily. And if it becomes 0, it's much easier to compress. The reason it's going in a zigzag is because the top part of the image, the top part of the black and white checkerboard stuff, that is more important. And you will tend to get more zeros in the rest of it where it comes to later in the zigzag pattern. To get it back, you just multiply by okay, this is getting technical. But JPEGs tend to break shellcode because the DCT part and mangles stuff, even if you're at the highest quality setting. If you look at the left thing, that's the original code, and after you JPEG mangle it, you end up with what you got on the right, which isn't at all what you asked for. So trying to run that, it will just crash. There's certain instructions which you can encode at certain positions without them ever being changed. So aligning where you put it is important. Maximizing the JPEG quality definitely does limit the amount of loss, but it makes big images. You can actually improve the compression though by scaling up by a multiple of 8 in each direction over just some other random value, just because it works on 8 by 8 squares. We did write a decoder stub which is JPEG safe, as I mentioned before, but it's not very useful at all, and it was just for proof of concept. There's a lot better way of doing it. If you use the right color space, a good quantization table, and you store it in the right shape, shellcode can be inserted without it being modified. As I said, the JFIF file, which is a JPEG format information file, image file, uses the YCBCR, which covers a different range of colors than RGB, which is what everything will get converted to when it's displayed on your computer. The color space is lossy. It will tend to lose the least significant couple of bits from many of the bytes. And there are colors which can't be converted due to the way the format works. Like a 16.8 million color image, which covered all of the colors available for 24-bit. After I converted it into the YCBCR space and then back into the RGB space, only had 2.6 million colors. So that's about 1/8 of the colors disappeared. They're outside the color gamut for that. But you can sometimes, depending on the tools you use, encode your JPEGs with RGB color space. And you have to have the right shape. If you scale as I said, scaling the image to some multiple of 8 by 8 times its current size, until it's big enough to fit in memory, do that. JPEGs, they work on those blocks. If you don't use smoothing, the compression gets helped. I think I mentioned that already. The image here, you can now decode that entire block with only one DCT coefficient per block. If you look at how the basis function in the top, if you remember the top left-hand corner of it, it was all one shade. It's because it encodes the average color and none of the frequency components. So if it's just a single square, it's just going to be one value set, and the rest of the coefficients are going to be 0. So, and then if you choose where to put the shellcode, with Internet Explorer, if you put it in the top right, then you got the whole image to go through as an OPS LED. It does it from bottom to top rather than top to bottom like other programs do, and I don't know why. And then you saw 8 copies of it, one on top of the other. Yeah, okay. Why do we want to stack 8 copies of the shellcode? Well, because it works. That's the short answer. Here's the longer answer. Basically, it's for the same reason as you can do as encoding it with just 1 byte from as while you break it into 8 by 8 and you can encode it with just one DCT basis function coefficient. A constant value degenerates to the case where the average value is only one you need. However, with this, each 2-dimensional DCT basis function is actually the product of 2 1-dimensional basis functions. The horizontal component and the vertical component. If you don't actually have a horizontal component, it just becomes 0. So if you have a series of stripes, which, let's see, should I change the mouse color? Series of stripes like this. You can see that the coefficients on the bottom square where it's moving the dots along, it's only on the top row where the values are stored. That means we only have to store 8 values instead of all 64 values to store the stripes, which means we can, it has less chance for making a mistake. Okay, yeah, I'll make it a bit easier. The 8 by 8 block, basically, if you've got less stuff to add up, there's less chance of it making a mistake. That's basically what the stuff at the bottom says. It's, yeah, a little technical, sorry, so here's a demo. This is the output of my one. It doesn't quite look as pretty as Michael's, but what I did was download a file, just a random one off the web, ran the script over it, which is what JPEGSPOC, the actual program you run, is called, and copied that to vartemp. So you see the output of it, very pretty, tells you what's going on at every step along the way. It automatically picks a good scaling size for you that takes up a certain amount of memory. And yeah, you end up with a 3 meg JPEG, which actually compresses quite well with if you use mod gzip. So as I run it, first we load it up in IE, and yeah, it takes a little while to load. It's the quality on this. Some of it's due to the AVI, and some of it's due to the image itself. Then open up Ollie. Because we haven't used any exploit, I've used Ollie debug to actually run the code. So I'm just going to move the EIP to the right place in there. So we select that, open it, wait for it to load. Yep, and then we start it running again so we can get rid of the debug thread, make sure it's still there. Yep. So yeah, the colors, yeah, the flowers look nice. So. Okay, and then we have a look at the memory map, sort by size, and our one's right at the top because it's the biggest one. The amount of space that takes up is about 175 meg. So that's a huge target for us to aim for. So I just copy the address, and we'll have a look at that in the data. And yeah, that's the code we want, and it takes up a large amount of space, like from OX 20, I think it was around OX 200020 to a big amount, so add 175 to that. We don't actually get to see my shellcode because I didn't scroll down far enough because it wouldn't fit on the screen because I resized it. So yeah, it takes a huge amount of space up, and I couldn't be bothered scrolling all the way to the bottom. Over here, if we go to that address, and see I've done it before, there we go. That's the actual code it's going to execute in there. So those instructions, like the rest of the instructions that follow up for the next 175 minus the size of the shellcode length, are all don't do anything instructions. Basically, they'll just say, yeah, move some register to another register, add something to that register, subtract it, things like that. And I tell it to run. And yeah, it doesn't like you telling it to run data, so it gives you a warning. But and then it's running, and I have to change to IE, and it pops calculator. So yeah, sometimes you need to tell it to activate the component. I think it was in the wait for multiple objects or something. So what you just saw was just provide exploit, a proof of concept. Yeah, I simulated the actual exploit itself using Ollie, and also so you could have a look and see a little bit about what the shellcode looked like. And some of it requires some extra tools. So these notes here, if you decide to download it, it was developed using Cygwin and in the Windows environment, and they managed to break X, or break ImageMagick at some point. But there's a workaround for that, which was posted somewhere. And the output's only for our 24-bit displays on Windows, because that's the most common target, really. And other platforms and bit depth, yeah, exercise for the reader.
So I tackled PNG.
So how do you detect these type of things? And how do you stop people detecting these type of things? And how do you stop people stopping detection? Basically, you can look for big files. But compression is really good on these files. I made a 8K by 8K light gray image with shellcode. So it was 192 meg uncompressed. The PNG format of that was 83K. And then when it was transferred using mod-gzip, it was just over 1K. So it's not going to be a large file. However, you're going to have it quite a bit larger with an actual image stored into it. That was probably the most redundant case you could have, so it compressed the best. The images tend to be larger than a normal file, but not hugely so. They're scaled up images, which just means they've got a lot of redundancy added, and that's what compression gets rid of, just the redundancy. So you're repeating the same stuff over and over again, and it just compresses it pretty well. The filtering also reduces the total information which is stored in the information. The filtering to make it so you only have valid no-op bytes. So rather than have the full range of 256 values each pixel can have, you have quite a bit smaller than that. There tends to be more bits overall in an image than the same image which has been scaled up. But so overall, they're slightly larger. You could look for images with large dimensions. But assuming you can read through the mod-gzip, then yeah, that would work against the method we've described. But if you make the image half the size in each dimension, you can just use 4 images. Or if you make it a third, you use 9, or use 4. Well, it's not quite that simple. There are some other tricks you need to use, like using quite a few more images, just because of the way memory allocation works. You could look at, basically, we remember the byte frequency graphs from before with the spikes and that unknown hacker. The histograms, they were for normal images and the no-op sleds, and when you looked at those, they looked totally different. But if you knew where you're going to land in the image, you can only modify the parts which are before that to be it, and you can have the other parts cancel out any problems in it. You can tell roughly where you're going to land in an image also using page alignment tricks. Basically, you only have to know the last 3 bytes of where you're going to land. And if you repeat only the modifications over the parts after where you're going to land, and you repeat that every page size, you can just keep the rest of the page the same and just modify everything to cancel out the analysis they could do. However, you might be able to then slice up the image and analyze each slice independently, look for variations in the variations on there, but then you're just starting to get to a lot of work, which isn't going to help much. Your IDS would have to be very smart and very smart, because you need to know what the targeted program is and how the targeted program is going to handle that particular image format. I mentioned very briefly earlier the gamma chunks, which are the color correction stuff. These control how things brighten as the value increases. Right, so it changes basically the rate at which the brightness grows. What's the default gamma for the target application if you haven't got one in there? Does it actually read it from the file if you specify one? What if the file is slightly malformed, like you've got 2 gamma tags, or you put the gamma tag after the image data? And does it handle it correctly, or does it do something weird? And what about alpha, which is the transparency? Adding stuff like that to it, where does the compositing happen? Where does it mix it with the color underneath? And what is the color underneath? And how many files which expand to over 100 megabyte, all of which could have shellcode in them, can your IDS system analyze per second, compared to how many, If your IDS can emulate the browser, can you own the IDS at the same time? You also might be able to use some techniques which are mentioned in the paper on which is called language trees and zipping. It was basically, the idea was they used gzip on a bunch of texts from different authors, and were able to identify the authors just by the compression ratios. They got a 93% success rate, and I think 93% for an IDS is probably a bit low. But it should be really easy to do. A 15-year-old won a science fair using this technique. He basically demonstrated that William Shakespeare could have been Christopher Marlowe by using this technique, and if you don't know who either of those people are, you should Google. It's good to get culture. Each of these interesting file types is already compressed. which it may save some effort, both for you and for the IDS, if it works. PNG uses zlib, which is the same type that they use with the gzip compression. GIF uses LZW, and JPEG uses the Huffman encoding on the coefficients. So you've already got the compression happening for you, so that may help. What else can you use a big file for? You can create arbitrary structures with pointers in them, which point to valid locations. I said before, I was talking about the changing the last three numbers of an address. I don't think anyone knew what I was talking about. Okay, in any address which ends in XYZ, every time you repeat it over 4K, the XYZ is going to be, you can make that reference the same structures. So then you can create just about any structure, and even those which need valid pointers to other structures, using the same idea as where you land your shellcode. You can predict the memory range which is going to be available. You can't make this necessarily blend into the image with just any old structure, so you could use other tricks. Like one thing that works, which is kind of cheating to call it pun code, is to put in a background image which is larger than the screen. So it actually renders it off screen. Or what's the shortest shellcode that you can use to do anything useful? A 2-byte jump to yourself is a good infinite loop shellcode. But what's the longest? When you why do you want to have all your shellcode in one place? If you use the same thing as the structure technique, the one where you use the last 3 numbers of the address, you can know where you are in your image. You can basically convert everything into a not palette, and you can just convert that part of the image that you want to land in to the right type of thing, and from any location you land in, you know where you are relative to the rest of the image. You can hide that using those, we showed the blending from grayscale. You can blend stuff in with its surroundings using the same general techniques as that, where the transition to shellcode actually occurs. Why use one instruction when you can use 1,000? You could de-optimize your code, make it really difficult to analyze, but it's able to be done automatically, and then you can get colors which match up a lot better. You can have your whole image the shellcode, rather than an OOP slate. And then you can actually use some of those other values that are currently too dangerous. You can store some local values in areas. You can actually store your values in the image itself with self-modifying images. It would be interesting to play core wars using an image, so you have 2 threads of the program running on it. If you don't know what core wars is, you should look that up too, because it's... Yeah, this is the last no opposite example. And are there any questions?
Yeah, go ahead up front.
I just want to make sure I'm understanding correctly with respect to the JPEG images that you're using. Are you injecting your shellcode prior to the lossy compression portion?
Okay.
Yeah,
okay.
so the question was about the JPEG. Is shellcode being injected before the lossy compression?
Yeah, the image itself is being generated with the shellcode already in it when it's compressed. So the compression, the quantization values I'm using and the color space I'm using is chosen in such a way as it won't actually degrade it won't actually cause any lossiness in the shellcode itself, and the copying it so it's 8. So I put 8 copies one on top of the other. That in itself as well prevents it from being lost.
We'll take more questions. I just wanted to remind people, come grab a t-shirt on your way out. I worked really hard to carry these over here. I'm going to be really upset if I have to carry them back. But other questions? Feel free to come up and ask me the questions. Sorry, I just